So hey guys, as you can see from the thumbnail of the video that this video is going to be about the transpose of a graph. Okay, so transpose of a graph, like why did I choose to discuss about the transpose of a graph rather than Kosa-Raju's algorithm is because the Kosa-Raju's algorithm has one of the steps where we need to transpose a graph. Okay, and I thought that let us make a separate video for the transpose step altogether, because the Kosa-Raju's algorithm basically involves 3 steps. That is, like, you have to apply DFS 2 times, and one of the step is transposing a graph. Okay, so I thought that, like, why not discuss about the second step in a separate video, so you know what exactly does the transpose mean and what how do we actually implement that in the code. Okay, coming back to the topic, so here in this video we'll be discussing about the transpose of the graph. So before we actually jump into the definition of transpose of a graph, I would like to talk about these 3 terms, that is transpose, reverse and converse. Okay, so anywhere if you encounter these 3 terms, that is transpose, reverse or converse, they exactly mean the same. Okay, so in graph terminology, a converse is same as reverse is same as transpose. Okay, so these 3 words can be used interchangeably when discussing about the transpose of a graph. So that was a quick highlight about like if at all you find people using different words. So all of these 3 words mean the same. Okay, cool. So coming to the definition of transpose, so transpose of a graph G. So as you all know that a graph G can be represented by a set of vertices and a set of edges, where each edge would be in the form of this particular thing, that is U and V, where U and V are nodes and there is an edge going from U to V. Okay, so if you draw a graph and there are 2 nodes U and V, so you'll be able to find this type of edge in the graph, that is an edge from U to V will be present. Okay, so this simply means that now transpose of a graph G is a graph GT. Okay, so denoted by something like G superscript T. Okay, such that G contains an edge, that if at all G contains an edge UV, then GT should contain an edge VU. Okay, so what it simply means that if we have an edge something like 1 and 2, okay, so imagine that in our main graph 1 and 2 are the nodes and we have a directed edge something like 1 and 2. So here you have the movement from 1 to 2 possible, that is you can move from 1 to 2, but then movement from 2 to 1 is not possible. So if at all we have an edge something like this, that is between 1 and 2, the graph of GT, okay, so the transpose graph of this particular graph denoted by G superscript T, it will be having an edge something like this, 2 and 1, and you'll have the edge something like this. Okay, so if you just closely observe that the transpose graph will be having the edge in a reverse direction. यहाँ पे 1 to 2, so यहाँ पे हमारा 1 से 2 के बीच में edge था, तो transpose के बीच में 2 से 1 के बीच में edge होगा. ठीक है, so something like this, so 1 to 2 and उल्टा कर दो arrow, यहाँ पे 1 and 2 same रहेगा and उल्टा कर दो arrow. Okay, so यहाँ पे transpose मिल जाएगा. Same thing you need to do with all the edges. So if you had an edge between 1 and 2, then 1 and 3, something like this. So in the transpose you will have an edge between 2 and 1 and 3 and 1. Okay, so something like this. So you just need to reverse the edges. Okay, the number of vertices, they remain the same. The space occupied by the graph, it remains the same. Only thing that changes is the direction of the edges. That is U V के बीच में edge था, अब हमने V और U के बीच में edge बना दिया. That's it. Okay. So as you all know that the graphs can be represented in terms of an adjacency matrix as well as an adjacency list. Okay, so this is a sample adjacency matrix of a graph, and this is how the adjacency list of a graph looks like. Okay, so and these 2 graphs are different. Here we have a graph of basically 3 nodes, and here we have a graph of 4 nodes. Okay, so let's discuss them one by one. So let's take a look at the adjacency matrix graph first. Okay, so if you just closely take a look at this particular graph, so if you were to draw this graph, right, so how would you draw it? So we have 3 vertices over here, so 0 1 2. Okay, so 0 1 2, if at all we draw it something like this, so we have 0 1 and 2. Okay, and what all edges are there? So we'll say that between 0 0 there's an edge, between 1 and 1 there is an edge, between 2 and 2 there's an edge. So it will be something like these kind of edges. Okay, so let's ignore these kind of edges, and let's focus on the edges that are going from one node to a different node. So how do you read this particular graph? So on the left hand side you have the source vertex, and on the right hand side you have the destination vertex. Okay, So it simply means that if you have a vertex from U to V, right? If you have a vertex between U to V, all the U's would be present on the left hand side and all the V's would be present on the right hand side. Okay, so on the top. And I hope that you already know how to read a matrix. Okay, so this would be array of 0, 0. This would be array of 0, 1. This would be array of 0, 2. Then you have 1, 0. So this would be 1, 0. And then you have 1, 1, then 1, 2, etc., etc. Okay, so here we see that we have an edge between what all? So we have an edge between 0 and 2. Okay, so we have an edge between 0 and 2, something like this. Okay, so it is a directed edge, right? So we have an edge between 0 and 2. 0 is the source and 2 is the destination. Then again, what else do we have? So we have an edge between 1 and 2. Okay, so this particular block, so this corresponds to the block number 1 and 2. So we have an edge between 1 and 2, something like this. Okay, and all the ones that are present in the diagonals, so they basically refer to these kind of edges. Okay, so that is, you can move from 2 to 2, you can move from 0 to 0 and something like that. Okay, so now when we are talking about the graph transpose, right? Okay, so this was our graph, and when we are talking about the graph transpose, okay, so this is our G, and when we want to derive a GT, what do we need to do is we will write down the vertices as it is. Okay, so 0, 1 and 2. The simplest way is to basically write the vertices as it is. Okay, so 0 was here, so I wrote 0 here, 1 was here on the left hand side, I wrote 1 here, and then 2 was on the right hand side, I wrote it simply like that. Now simply what you need to do is you need to reverse the edges. Okay, so यहाँ पे zeros, so यहाँ पे you can see that यहाँ पे 0 से 2 के बीच में edge जा रहा है. So for this edge, the source node is 0 and the destination node is 2. Okay, so we just need to reverse this. Okay, the source need to be 2 and destination need to be 0. Okay, source need to be 2 and destination needs to be 0. Okay, so you'll have an edge something like this, but then the arrow would be reversed. Okay, so 2 is the source and 0 is the destination. Similarly, for this particular edge over here, we have an edge between 1 and 2. We need to put the same edge, but then reverse the arrow direction. यहाँ पे right hand side में था, यहाँ पे left hand side में कर देंगे. And for all the edges that go to itself, if you have an edge between 3 and 3, okay, so if you were to split it up, right? So an edge edge between 1 to itself is something like this. Okay, 3 and 3. If you reverse also, it will be 3 and 3 only. Okay, so this kind of edge always remains the same, right? Okay, and now when you want to plot this particular graph, that is G transpose into a matrix, so we'll have the following kind of matrix. So you have, okay, so here we have the source and then we have the destination. So this would be 0, 1 and 2, 0, 1 and 2. So we have an edge between the node to itself. So we'll put all the ones in the diagonals. Okay, so an edge to itself, and then we have an edge between 2 to 0. So 2 to 0, 2 and 0. Here we have it, and then we have between 2 to 1. Okay, so 2 to 1, we will have another edge over here. Okay, and rest we do not have any edges, so we'll put 0 in all the other blank spaces. Okay, and this is the transpose of this particular graph over here. So for the adjacency matrix, what we need to do is we need to iterate from all the nodes over all the nodes I plus plus, and for j is equal to 0, j less than total nodes, and j plus plus. Okay, the transpose graph, right? The transpose of I j would be equal to the main graph, that is G, the graph of ji. Okay, and if you basically do this particular operation, right, you will get a transpose graph for an adjacency matrix. Okay, so as you can see over here, the algorithm for finding the transpose of an adjacency matrix is pretty straightforward. All the edges which are going from I to j, okay, so all the edges that are going from I to j, so you are simply converting them to the edges going from j to I. Okay, and that's about the adjacency matrix. Okay, so next let's move on to the adjacency list representation of it. Okay, so consider this particular graph over here. So we have a graph consisting of 4 vertices. So the total number of vertices is 4 over here. Okay, so the total number of vertices is 4 and the total number of edges are 1, 2, 3, 4 and 5. Okay, so total number of edges is 5 over here, right? And you can see that there are arrows associated with the edges, and hence we can see that these are directed edges, right? Now when we want to find the transpose of this particular graph, so as we have like iterated a lot many times in this video only, that in order to find a transpose, okay, in order to find a transpose, what we need to do is we need to write the vertices as it is. Okay, so I'll write it as 0 in the middle, then you have 1, then you have 2, and then 3 over here. Okay, so here I just wrote all the vertices. Okay, so the total number of vertices remain the same for a transpose graph. There's nothing to say about it. Only thing that changes is the direction of the edges, right? So 0 से 1 यहाँ पे, here you can see that यहाँ पे 0 से 1 पे जा रहा था edge, तो हमको क्या करना है? Simply we have to reverse the direction. 0 से 1 जा रहा था, अब 1 से 0 कर देंगे, ठीक है? यहाँ पे हमारा 1 से 3 जा रहा था, अब 3 से 1 पे कर देंगे edge, right? And यहाँ पे 3 से 0 जा रहा था, so 0 से 3 पे एक edge डाल देंगे ऐसे, right? And then you have 2 to 3, then we'll put an edge between 3 to 2. Then here we have an edge between 0 to 2. I'll put an edge between 2 to 0. Okay, all the directions I've reversed it basically, right? And this is the transpose graph for an adjacency list, right? So from the diagram, it's nearly the same as the adjacency matrix. But then when we are doing in the code, right? How do we actually write the code? Okay, so this particular graph G 0, 1, 2, 3, and then all these particular edges can be represented in the form of this adjacency list. Okay, so this would all be the source node, and there's an edge between source to all the destination. It simply states that 0 का neighbor कौन कौन है? So 0 का neighbor है 1, 0 का neighbor है 2. Here we have 0 से 1 पे edge जा रहा है, 0 से 2 पे edge जा रहा है, ठीक है? That's what it is representing over here. Now from 1, where are the edges going? So from 1, we have an edge only to 3, and that's the reason why 3 is present in the adjacency list. Okay, so I assume that I do not have to basically focus a lot on like how adjacency lists are represented. You can refer to this particular video to understand more about the adjacency list. But then what I'm going to talk about here is how do we find the transpose of this particular adjacency list. So as you can see, we have an edge between source and destination over here. So simply all the source to destination needs to be converted from destination to source for a graph transpose, right? So here we have an edge between 0, 1 and 0, 2. So what we need to do is we simply need to iterate over this particular list, right? So this list, then this list, then this list, okay? So for every source node, uska jo neighbors hai, we need to add an edge between the neighbor and the source node, okay? So we'll have something like graph of neighbor So we'll have something like graph of neighbor dot pushback source. Okay. So graph of neighbor dot pushback source. So if at all we do this particular operation for all these elements, then we'll get the transpose of an adjacency list. So 0, 1, 2, and 3. So these are all the source nodes. So as I told that vertices remain the same. Graph में क्या होता है? बस directions change हो जाते हैं edges के, and that is what we are going to do over here. So now 0 से 1 पे अपना जो edge था, so in the main graph we had an edge between 0 and 1, right? So this one we need to reverse it to 1 to 0. ठीक है? So in order to do that, okay, in order to establish an edge between 1 to 0, we will be adding 0 in the adjacency list of 1. Okay, so यहाँ पे 0 आके बैठ जाएगा, right? Similarly, we had an edge between 0 and 2 in the main graph, so we need to establish an edge between 2 and 0 in the transpose graph. 2 and 0 में edge establish करना है तो क्या करना है? 0 को हम 2 के list में डाल देंगे. And remember that here we are constructing the graph transpose, the transpose of the graph. And here we have the destination, here we have the source, then you have destinations. Okay, so all of these are adjacency list, and we are going to fill all of them one by one. Now, so this particular thing is complete. That is, we have established from 1 to 0, then 2 to 0 we have established. Now we need to establish an edge between 3 and 1. Okay, main graph में 1 and 3 के बीच में था. Now we have to establish between 3 and 1. Now 3 and 1 के बीच में establish करने के लिए we have to put 1 in the neighbor list of 3. ठीक है, so this is also complete. Now we have between 2 and 3 edge है, तो 3 and 2 के बीच में डालना है. So 3 and 2 के बीच में डालने के लिए हमको 2 को 3 के neighbor list में डाल देना है. Okay, so 1 and 2 basically sits over here. So this is also complete. Now we have an edge between 3 and 0 in the main graph. Now in the transpose graph, we will have an edge between 0 and 3. Okay, so 0 and 3 में edge establish करने के लिए we'll have something like this. We need to put 3 in the neighbor list of 0. Okay, and now since everything is done, I'll basically close all this set, and this is what we call the transpose of the graph. Okay, this is graph transpose. Okay, transpose. So basically, to summarize, how do we find the transpose of an adjacency list graph? We simply need to iterate over the neighbor list. Okay, for every source node, we run a for loop over the neighbor list and add an edge between the neighbor and the source node. Okay, so we have an edge between source node and all the neighbors. Now for all the neighbors, we need to add an edge between the neighbor and the source. Okay, just reversing the direction. Right. So next, let's jump into the code. Okay, so I hope that this particular concept of like how do we find the transpose is clear to you. I know it is very basically long explanation for a simple concept of transpose, but then I want you to understand it thoroughly so that when we are discussing Kosaraju's algorithm, you have basically no doubt at all like what exactly are we doing in this transpose step. All right, so let's jump into the implementation part of it. So here, as you can see, I have opened my Visual Studio Code editor. Okay, so first what we'll be discussing over here is how to find a transpose of a graph when it's an adjacency matrix representation of a graph. Okay, and let's do one thing. Okay, so first what I'm going to do is I'm going to declare the total number of vertices. So constant int total nodes. So this would be the variable that would declare like how many nodes are present, right? So here we have the total nodes to be equal to 3. So the example that I'm taking over here is this particular thing. Where is it? Yep. Okay, so this particular graph we are going to construct, that is 0, 1, 2, and this edges would be present. And for the transpose, we need to get an output something like this. Okay, so we will try to make this particular graph. Okay, so total number of vertices here is 3, right? So here I've declared a variable called constant int. So constant int total nodes is equal to 3. Okay, and for adjacency matrix, if you remember that we have an add edge function, something like this, so void add edge. Okay, and here we need to take in the graph. Okay, first as a first parameter, we need to take in the graph. So here it will be total nodes. Okay, and for adding an edge, what all information do you need extra? Okay, so between what and what nodes are we establishing an edge? Okay, so that would be the source and the destination information in source and in destination. Okay, so this particular information we need, and we simply need to do one thing. So here we simply need to add graph of source and destination. Okay, graph of source and destination is equal to 1. Right, so with this particular sentence, so with this particular statement, it will put a 1. Okay, so here as you can see, it will put a 1 in the graph of source to destination. So here if we have 0 to 2, right? So 0 and 2 ke beech mein we have an edge. So graph of 0 2, we need to make it 1, and that's exactly the same thing that I'm doing over here. The graph of source source of destination is equal to 1, and that is how you basically add a directed edge, right? So here add a directed edge to the adjacency matrix, right? Now let's declare a helper function which can basically print our graph. Okay, so we'll have something like required print graph, and here the input would definitely be the graph itself, and here the input would definitely be the graph itself with total nodes. Okay, so total nodes. And how do we print it? So I'll just do a cout statement, something like graph is. Okay, graph is, and I'll just run a for loop between int source is equal to 0, source less than total nodes, and source plus plus. Okay, source is equal to 0, source less than total node, and source plus plus. And for every destination, we'll check whether that particular value is 1 or 0. Okay, so int destination is equal to 0, destination less than total nodes, and we'll have destination plus plus. Okay, and we'll just simply print out what value stored it in graph of source comma destination, that is whether it is 0 or 1 or something like that. Okay, so we'll have graph of source and destination. Okay, so this would print that, and let us leave a space between every 1 and 0 that is present in the same line. And after we print a row, right, we need to leave a line as well. Okay, so that next set of rows would be printed in a new lines. Okay, so this is our print graph function. Okay, so this would print the ADJ matrix representation of the graph. Okay, of the graph. Right, so now we have the print graph function as well. Now let's do one thing. Let us establish our graph first. Okay, so we'll have something like graph, and here I'll declare total nodes comma total nodes. Okay, and what I'm going to do is I'm going to initialize all the values to be 0. Int source is equal to 0. So same thing, what I'm going to do is I'm just going to copy this one over here and initialize all of them to be 0 initially. Okay, so source is equal to 0, and graph of, instead of cout statement, what I'm going to do is I am going to initialize all the values to be 0. Okay, so in graph of source of destination is equal to 0. Let us also declare another variable to store the transpose of the graph. So this also would be have the same number of nodes, so total nodes of total nodes. And so in the same loop, let's also initialize all the elements in transpose to be 0 as well. Okay, is equal to 0. Right, now we will call our add edge function. So what all edges are present over here? So we have an edge between 1 and 1, 2 and 2, 0 and 0. So that is like self edges. So we'll have something like add edge. Okay, and we need to pass in the graph first, and between let's add all the independent nodes first. So 0 0, 1 1 and 2 2. Let's add them. 1 1, 2 2. Okay, so all these are self edges, right? So these this and this are established now. Now we need to establish the edge between 0 2 and 1 and 2. Okay, so we'll have add edge graph 0 2 and add edge graph 1 and 2, right? So 0 2 is there and 1 and 2 is there. Okay, so by this time we should have our edge established. So let us try to print our graph first. So print graph, and let us print the graph first, so that let's verify whether our graph looks exactly like this or not. Right, so let me open this one, and G++, I'll say transpose .cpp and /a.exe. Okay, so here we can see that 101, 011 and 001. So 101, 011 and 001. Okay, so our adjacency matrix is represented properly. Now what we need to do is we need to have a function that can transpose this graph. Okay, so transpose graph, let's have a function called transpose graph, and we will pass the original graph and the transpose graph variable. Transpose graph variable. So this transpose graph function is responsible for taking the original graph and the empty transpose wala variable, and inside that function it should basically do the processing as to basically establishing an edge between for every edge of the type source to destination. This transpose graph function will establish an edge from destination to source for the transpose graph. So how this function would look like? So we have void transpose graph, and the first parameter is obviously the graph, so graph, and this would be total nodes, and we'll have the another variable that is the transpose and total nodes. Okay, so when you're passing these two variables like this, right, so it is by default, like whenever you change any of the elements in these two matrices, it directly gets changed over here as well. Okay, it's not the copy that is getting modified, but then it's the actual variable that is getting modified. So here what we need to do is we simply need to run a for loop over the main graph. Okay, so for int source is equal to 0, I'll say source less than total nodes, and we have source plus plus, and for int destination is equal to 0, destination less than total nodes, and destination plus plus. Okay, and what we need to do is transpose of source of destination, transpose of source and destination, right? Transpose source of destination is equal to graph of destination of source. Okay, for we see that for every edge like source, for every edge like source to destination, we need to have an edge of destination to source. Destination to source in our transpose graph, right? And that is what exactly this particular statement is doing over here. So if at all you're getting confused, what you can do is you can simply say destination and source is equal to source and destination. Source and destination. Okay, so transpose of destination source for every edge like source to destination in the main graph, we need to have an edge of destination of source in the transpose graph. When this particular function is executed, this transpose variables will this transpose graph will get modified, and let us print the transpose graph over here as well. Okay, so print graph transpose over here, and let us print the main graph as well, and let us put the cout statement so that we can differentiate between the graphs. Okay, so cout main graph g is will print the main graph, and then we'll print the transpose graph. Transpose graph gt is, and this print graph of transpose will print the transpose graph, right? So let us run the program. So we have g++ transpose.cpp. Okay, and I'll do /a.exe. Right, so here we can see that the transpose graph gt looks 1 0 0 0 1 0 and 1 1 1. Okay, let's compare it with what we have in over here. So we have 1 0 0. Let me get the output as well. Right, so here we have 1 0 0, that is 1 0 0 0 1 0, that is second row is 0 1 0, and then we have 1 1 1 in the last row. Okay, and this is how we find the transpose of the adjacency matrix representation, right? So this was that. Now what we'll do is let us find the transpose of adjacency adj.cpp. Let me create a new file, and I'll say solve, and all right, so here what we are going to do is we will be doing the same thing, that is the transpose program. The very first thing let's do is let us establish the graph first. So we'll have vector of int graph of total nodes. Okay, so this total nodes variable is something we need to declare over here. So constant int, and which graph are we going to make over here is this graph, right? So this graph over here, that is, we have total nodes to be 4, and these are the edges that are present in this particular graph, right? So what we'll do is constant int total nodes is equal to 4, and for adding the edges we need to have an add edge function. So we'll have add edge, and the first parameter obviously would be the graph itself. So we have vector int graph, and between what all do we need to establish that? Between source and destination. So we have int source and int destination. And we need to establish a directed edge here. So only one statement of graph of source dot pushback destination would be present over here. So we have graph of source dot pushback destination. Okay, so if you're still confused about like how adjacency list representation, like all these add edge functions, etc. work, you can check out my video on the adjacency list representation. It is a pretty detailed video, and it will give you a lot of insight about the adjacency list representation of the graph, right? So here the add edge function is complete. So similar to adjacency matrix, let us have a print graph function as well, so that we can see like what exactly our graph looks like. So we'll have void print graph, and obviously the graph would be the first parameter, print graph the thing, and this graph we simply need to print it line by line, wherein you have the source node. So how do we print this adjacency list? So we'll have let's have it printed something like source node is, and the source node here, source node, and the adjacency list here will represent it something like this, like all those 1 2 3 etc. like whatever nodes are present, let us have it space separated over here, right? So what we'll do is we'll say for int source is equal to 0, source less than total nodes, and source plus plus, right? So we will be going through all the vertices, And for all the vertices, we will be accessing the vector associated with that vertex. So what we do is for int neighbor, okay, so neighbor would be present in the adjacency list. So here, if you just see, right, so here for 0 we had 1 and 2, for 1 we had 3, for 2 we had 3, for 3 we had 0. Okay, so these are all the vector of int, and we need to access this vector of int. Okay, and how do we access that? So we will have something like graph of 0, right? Graph of 0 will give you 1 and 2, graph of 1 will give you 3, graph of 2 will give you 3, something like this. So we'll have something like for int neighbor in graph of source. Okay, so graph of source. Okay, so graph of source will like turn by turn, it will have graph of 0, graph of 1, graph of 2, etc, etc, and we will be running a for loop on that particular list, right? So for int neighbor graph of source, we will be printing the neighbor. Okay, so we have neighbor, and we'll leave a space as discussed over here, and this particular line we can print it over here. Okay, so we'll have a cout statement, and we can say source node is spacebar and the source node, and we need to leave an empty line over here and print the space separated neighbors. And after all the neighbors are printed, let us leave another line so that the next cout statement goes in the new line, right? So this is our print graph function. And now what we need to do is let us establish the edges in this particular graph. Okay, so what are the edges present in this graph? So we have an edge between 0, 1 and 1, 3. Okay, so I will call the add edge function, add edge graph 0, 1. Okay, so 0, 1 is done. Let me mark it as well so that I don't forget. Okay, so 0, 1 is done. Then we have between 1 and 3. Okay, so add edge graph 1 and 3. Right, so 1 and 3 is done. Then we have between 3 and 0. Okay, so add edge graph 3 and 0. Okay, so we have an edge between 3 and 0. Then we have an edge between 2 and 3. Okay, so we have an add edge between graph 2 and 3. Okay, so between 2 and 3 we have established the edge, and between 0 and 2 there's another edge. Okay, add edge graph of 0 and 2. Okay, so graph of 0 and 2. So how many edges did we establish? So we have 1, 2, 3, 4 and 5. Here we have 1, 2, 3, 4 and 5. Okay, so another point to be noted here is that this particular order, it matters a lot in a directed edge. That is, you're establishing an edge between 0 and 1, and you cannot write this one to be 1 and 0. Okay, so you cannot write something like this for establishing this edge in an undirected graph, right? So in an undirected graph, this kind of behavior would have been acceptable, but then when you're dealing with directed graphs, make sure that this particular order you're taking care of. Okay, so 0, 1 is not the same as 1, 0. Okay, so this point just keep in mind. Now we have established all our edges. Now let us print our graph. Okay, so we'll print the main graph first. So print graph, and let us pass in the graph first. Okay, so print graph of graph, and let me say g++ transpose, and this one is adjacency.cpp. I'll execute it using /a.exe. Okay, so here we can see that the source node is 0, and we have an edge between 1 and 2, then 3, 3 and 0. Okay, so it's the same as this over here. Where is that? So here, if you can see it clearly, then here we have 0, 1 and 2, 1, 3, 2, 3 and 3, 0. Let me open it side by side. So we have 0, 1 and 2, 0, 1 and 2, between 1 and 3. So 1 and 3, 2 and 3, so 2 and 3, and then we have between 3 and 0. So 3 and 0, right? So the graph is represented properly. Now what we need to do is we need to write a transpose function. Okay, so we need to write a function called transpose, and let us also declare. Okay, so let's declare a variable called transpose, and it will be the same as the graph. So we have transpose and the total nodes. So we will be declaring a variable called transpose, and we'll be having the same number of nodes as the main graph. Now what we need to do is we need to call the similar function as how we did for adjacency matrix. We'll call something like transpose graph. Okay, and we'll pass in the main graph and the transpose graph as well. Okay, so and this function should be responsible for adding the necessary edges to the transpose graph. as of now, this transpose graph is empty, and this add edge function basically had added an edge in the main graph, right? So in the transpose graph, let us declare that function. So we have void transpose graph, okay, and the main graph will accept as the first parameter, and then we have the transpose graph accepted as the second parameter, transpose. Okay, so we'll have something like this, right? So now what we need to do is we need to iterate over the neighbor list of the main graph. Okay, so we need to iterate over the neighbor list of the main graphs. And how do we do that? We'll do a for loop for int source is equal to 0, source less than total nodes, and source plus plus. Okay, and we go through each of the nodes present in the neighbor list, right? For int neighbor, in graph of source. Okay, so graph of 0, graph of 1, graph of 2, all of these are neighbor list. And for all the elements, that is for all the neighbors, we need to add an edge. Okay, so we need to add an edge, something like this: graph of neighbor dot pushback or the source node. Okay, so graph of neighbor dot pushback source node. So we have transpose. Okay, so in the transpose graph, transpose of neighbor dot pushback source. So this sentence is what we need to write for the transpose of a graph. Okay, and this is pretty much it. This is the function for transposing an adjacency list, right? So this transpose graph function we executed. Now let us print the graph. So basically cout statement doesn't matter, but then for clarity's sake, I'm writing it something like this. And now let us run this particular program and see what output do we get. Okay, so here similarly I'll do g++ transpose adj.cpp and /a.exe, right? So here we can see that the main graph, this one we had seen the output. Now the transpose graph, let us take a look at that. So the source node is 0, the destination node, basically this. So this is the adjacency list that we are getting over here. That is 0 and 3. Then we have 1 0, 2 0, and 3 1 and 3 2. So these are the edges that we are getting over here. So let's compare it with what we have in the diagram. Okay, so this is supposed to be the transpose graph of this graph here. And let me get the output side by side. Okay, so here we can see that we have an edge between 0 and 3. Okay, so 0 and 3, so this represents that. We have an edge between 1 and 0, so 1 and 0 पे एक edge है. Then we have an edge between 2 and 0, so 2 and 0 पे एक edge है, and there is no other edge going from anywhere. And then we have an edge between 3 1 and 3 2. Okay, so 3 से 1 पे एक edge जा रहा है, and then 3 से 2 पे एक edge जा रहा है. Okay, and this is how we find the transpose of an adjacency list representation of a graph. Okay, so this was pretty much it about the transpose of a graph, and we will be using this particular concept in the Kosaraj's algorithm that we are going to be discussing next. So I know that this was a pretty simple and straightforward concept, but then an understanding of this concept is very useful when you're dealing with different algorithms in graph. Okay, so thanks for watching and see you in the next.